I'm Professor Brad Fulton, and welcome to my Stats podcast. This is an edited audio recording of my course. Each lecture is its own episode, and there's a total of 24 lectures. This course provides an introduction to the quantitative methods social scientists and data analysts use to collect and evaluate empirical data about society. Through this course, you will learn to gather, describe, and analyze data with an emphasis on the application and interpretation of these methods. This course will also help you to be a more informed and critical reader of academic research, public opinion polling, and advertisement claims that present statistical evidence. Although some of the current events I reference might be dated, the content is timeless. I hope you enjoy this lecture, and if you have any questions, you can email me at bradrfulton@gmail.com. Hi, my name is Professor Fulton. If you like this podcast, you'll love the book I use for the course. It's titled Statistics, Unlocking the Power of Data. This book uses a highly intuitive approach to help students visualize statistical concepts, which accelerates understanding. I've reviewed dozens of textbooks, and Unlocking the Power of Data is hands down the best one out there, mainly because of its unique intuitive approach and straightforward explanations. You can find a link to the textbook in the show notes, and if you use the promo code BLOCK5, you'll get a 10% discount. As a reminder, the first exam is going to be Wednesday, the 18th. This is all on the syllabus, so it's going to be in class, solving problems. You'll each get to have one double-sided 8.5 by 11 page of notes, but you need to prepare these notes on your own, and I'll actually have you submit them with your completed exam. But I'm mentioning this now in that it'd probably be in your best interest to start building this page of notes right now, taking the stuff that we've already covered and begin forming this page of notes. So this is the second lecture of hypothesis testing. The question that we ask ourselves when we're doing hypothesis tests is, what is the probability that our observed outcome could have occurred by random chance? So because we're only taking a sample of the population and we're making an inference about the whole population based on that sample, what is the chance that our sample has just a really skewed outcome? You know, this outcome that we get that we think, wow, this is amazing, like women exercise so much more than men. We still have to ask ourselves, what is the probability that this outcome we got could have just occurred by random chance? And there's actually really no difference between the amount of time that men exercise and the amount of time that women exercise. So that's why in statistics, we need to do hypothesis testing, because we're only looking at the sample to make inferences about the population. Another term that you'll be seeing in this course is p-value, and again, it's one that you don't use in everyday language, so I'm going to walk you through the definition of it. But I think p-value comes up a lot, and so it's good to be aware of what it is. The p-value is the probability of getting a sample statistic as extreme as the observed sample statistic, just by random chance, if the null hypothesis is true. It's the probability of getting a sample statistic that's as extreme as our observed sample statistic. And so the smaller the p-value, the smaller the probability. It's the stronger the evidence is against the null hypothesis and in favor of the alternative hypothesis. We use the randomization sampling distribution to calculate the p-value of the observed sample statistic. And so I highlighted this part in yellow because this is what you're trying to determine. So what I'll ask you is, what is the p-value of the observed sample statistic? Sometimes that's confusing. It's like, what is the p-value connected to? When do we use it? And it's when we're trying to identify what's the p-value of the observed sample statistic. It's the probability that you get an outcome as extreme as your observed sample statistic. Another way of saying it's the proportion of randomization sample statistics that are as extreme as our observed sample statistics. So I basically stated the definition 4 different ways, but you can read through this and begin to get your mind around it. If we do the exercise in gender study, this is what we did yesterday, where we had females and males, and then we had X bar was the mean number of hours spent exercising, and we were saying, do males exercise more than females? And then we created a randomization sampling distribution, and then clicked on right tail, and then I went right here and I plugged in the number 3 hours. Does anyone remember what 3 hours was?
The difference between male and female exercising?
Yes, that's our sample statistic. The difference in sample means was 3 hours. And so the p-value is the proportion of randomized sample statistics that are as extreme as our observed sample statistic. The proportion of sample statistics that fit in this range gives us our p-value. And so the p-value is this number. It's basically saying that in the randomization sampling distribution, 10% of the sample statistics were as extreme as our observed sample statistic. That's where we get the p-value, and this is the p-value of our observed sample statistic. Again, the p-value is the proportion of randomization sample statistics that are as extreme as our observed sample statistic. So the randomization sampling statistic is if we ran the study assuming that the null hypothesis is true, that there is no difference by gender in the amount of time exercising, and if we did that, how often would we get an outcome as extreme as the one we got in our observed sample? It's basically helping us to see how often would we get an outcome like this just by random chance. The way to interpret this is if time spent exercising did not differ by gender, we would see a difference in sample means as extreme as 3 hours in about 10% of our studies. So in a sense, we can't say with great confidence, yes, men exercise more than women, because 10% of the time, like 10% of our random samples would have revealed that men exercise more than women, even when there was no difference. Yeah?
I'm getting confused because it says, like you said earlier, the smaller the p-value, the stronger against the null
Yes.
hypothesis. But like, because I was going to say, if you had like 5%, it would be a smaller value, but that would make it stronger against the null.
Yeah. So it's confusing because a lot of times when you think smaller value, weaker evidence, but it's
because
actually
it's weaker evidence for the null hypothesis.
Yeah. Say our difference in sample means was like 8 hours, our sample statistic would be way out here, and the likelihood of getting a sample difference in sample means of 8 hours if there was no difference is like unheard of. It's off the charts. So it's like we can be really confident that the difference that we observed couldn't have happened by random chance. It's way out here where there's no randomization sample statistics that are as extreme as that one. Here's maybe a way to also think about an example. 2 different studies. The observed sample statistic from study A has a p-value of 0.002, and the observed sample statistic from study B has a p-value of 0.2. Which study provides stronger evidence against the null hypothesis? Okay, we have our observed sample statistic, and we want to know the p-value of that statistic. And so the way we calculate it is we create our randomization sampling distribution and generate a bunch of randomization sample statistics in a scenario where the null hypothesis is true. And then what we want to know is, in this distribution, how many of the sample statistics are as extreme as our observed sample statistic? And the fewer sample statistics are as extreme as our observed one, the stronger the evidence that this sample statistic couldn't have happened by random chance. The actual answer to this would be study A because it has the lower p-value and thus the stronger evidence against the null hypothesis. Because what it's saying is only 2/1000ths of the randomization sample statistics were as extreme as our observed sample statistic. There's 3 ways of looking at this with just the formal definitions, the example from exercise and gender, and then this one. To get it to sink in, read through all 3 of those and convince yourself and see the mechanics of this. So now we're going to do a similar scenario of what we did yesterday. Yesterday, when we did the study on exercise and gender, what type of study was that? There's 2 types of studies that we can do in sociology or social sciences. Do you guys remember the 2 types of studies? Experiment and observational. So what was yesterday's study? Why was it observational? We observed what was already going on in the natural world. We didn't say, okay, Chris, we're going to assign you the gender female. Brittany, we're going to assign you the gender male. Like we didn't assign treatments to anybody. And so it's just we observed it. We're going to walk through the same process but show how you do it with an experiment. The research question is desipramine effective at treating cocaine addiction? And so this is a experiment. It's a new drug that they're wanting to see if it's effective at curbing cocaine addiction. And so the way that they set up to study this, in a randomized experiment on treating cocaine addiction, 48 cocaine addicts were randomly assigned to take either desipramine, a new drug, or a placebo. Then they were followed to see who relapsed. So they basically found 48 cocaine addicts and randomly assigned half of them to take this new drug and the other half to just take a placebo. So what's our sample size? 48. Good. 48 cocaine addicts. What are the two variables that we're going to be measuring in this experiment?
Desipramine?
Yeah. One variable is what drug did you take? The desipramine or the placebo? And then what's the other variable? Relapse. So this is really important to look at something like this and be able to pull out what are we measuring or what are the parameters that we need to be tracking. So Tim said, what's the treatment given, desipramine or placebo, and then what's the outcome? Did they relapse or no relapse? Each person in the study was either given desipramine or a placebo, and then each person in the study either relapsed or didn't relapse. What are the sample statistics that we need for this study? What is the observed sample statistic that we're going to be testing to see if it's a significant result? Are these variables quantitative or categorical?
Categorical.
Okay, so then state the sample statistic in its...
Sample, like the sample proportion.
Yes.
I know how to like what to use, but I don't know how to put it into a sentence.
It's common, the pathway that Chris was going down, where you say, okay, what's the proportion of people using desipramine that relapsed, and how does that compare to the proportion of people using desipramine who didn't relapse? Well, that's sort of the same number, because if you have 60% of the people using desipramine who relapsed, we already know what proportion didn't relapse. It's 40%. That's the same thing, so you need to compare two different things. So like where we compare men exercise hours and women exercise hours. The sample statistics that we're interested in are p hat d, which is the proportion of people treated with desipramine who relapsed, and the other is the proportion of people treated with a placebo who relapsed. So research question, is desipramine effective at treating cocaine addiction? The null hypothesis is the claim that there is no effect or no difference. What would be our null hypothesis for this experiment?
Is that asking about the equation?
Well, okay, so every time that I'll ask for the null hypothesis, I want both the word form and then the equation. So, because you read through the different assignments, you'll get a feel for how people state hypotheses. And the reason this is actually a cumbersome way to state it, but it'll make it easy to do our equation by stating it this way, because basically what we're saying is desipramine is equally effective as a placebo at treating cocaine addiction.
So we say equally?
Well, equally, I did that intentionally because when we create the equation, it'll make it really easy. Whereas if I just said desipramine is not effective at treating cocaine addiction, and then I said, now create an equation for that, you'd be like, how do I create an equation for that? So both are true, both are accurate, but this just makes it easier to then do the equation. So whenever we state hypotheses, we're talking about the population as a whole, because we're using our sample to make an inference about the whole population. So the null hypothesis is that if we looked at the whole population, like say thousands and thousands of people were given this drug, would the proportion of people who relapse using desipramine minus the proportion of the people who relapse using no drug or placebo, does that equal 0? So it needs to be stated in terms of the population parameter. P hat D equals P hat P, or another way of stating it is PD minus PP equals 0. And this is the proportion of people who have relapsed. Okay, so then the alternative hypothesis is the claim that we seek evidence for. So desipramine is more effective than a placebo at treating cocaine addiction. Let's say we just took those 48 people and gave all 48 of them desipramine, and then look 2 years later to see how many relapsed, and only 10 of them relapsed. It might be that cocaine addiction really isn't as addictive as we thought, and people can naturally overcome it without desipramine. Let's say desipramine doesn't do any good, but just because of people's own self-will, they overcame the addiction. So that's why we have the placebo in there, because you're comparing it with a control group or a group that didn't get anything. So that controls for all these other factors that might help someone overcome cocaine addiction. So you do need a comparison group, and then your hypothesis needs to include that comparison group in it. The number of people who relapse using desipramine is ultimately going to be less than the number of people. So I point that out just because, like, one little switch of the sign. Okay, so we've set up a research question, we have our sample, we have our hypothesis, and so we have our 48 participants right here. We're going to just randomly place them in 2 different treatment groups. I didn't create this, by the way, but I think it's kind of cool. Through a random process, people get placed into 2 groups. This group is going to be taking desipramine, this group is going to be taking the placebo, and then we carry out the treatment phase. So however long they're supposed to take this drug, they do, and then 2 years later, we come back and we talk to them, and we check to see, are you still addicted or not? This is our observed sample statistic. This is the experiment that we ran. And with desipramine, 10 people relapsed, whereas with the placebo, 20 people relapsed. But as you notice, Chris, some people who are taking the placebo didn't relapse. So there's things out there that can cause people to not relapse that aren't associated with these therapies. So then our observed sample statistic is p hat d minus p hat p. The sample difference in proportions is negative 0.416. So does that support or contradict our alternative hypothesis? It supports it. So right now, we have one sample statistic, and it supports it. If it didn't support it, we could just end the study and be like, it's not any more effective. But because we get a result that falls within the range of like, yes, there is, it looks like it reduces relapses, we have our one sample statistic, and our best point estimate at how effective desipramine is that there'll be fewer relapses if people use desipramine. But that's only a point estimate, and we need to know how much does that sample statistic vary. So then that's where we go into the statistical test. So our observed sample statistic is p hat d minus p hat p. So this is the difference in sample proportions. And so then the question is, how unusual would it be to observe this sample statistic by random chance if the null hypothesis was true? So we take our observed sample statistic and we say, how unusual would it be to observe this sample statistic if desipramine actually didn't have any effect? In a world where desipramine just doesn't have any effect, what is the likelihood that we'd find a difference in sample proportions of negative 0.416? Another way to state it is, what is the probability that we would observe by random chance a difference in sample proportions as large as 0.416 if desipramine is equally effective as a placebo at treating cocaine addiction? To answer this question, we need a distribution of sample statistics that would occur if the null hypothesis was true. This is then going to the randomization sampling distribution. We generate these sample statistics using the randomization process. So then to reiterate the randomization process, yesterday we talked about pieces of paper with all the exercise hours on it, and then we just randomly assign male, female to those. It's a very similar process. We have the sample size of 48. So imagine having 48 pieces of paper, 30 pieces have an R on it, and 18 have an N on it. This corresponds with the total number of relapsers and non-relapsers in our experiment. You sort of pull back all your outcomes and you just put them back in as the total 48. You combine them. As a total, 30 people relapsed and 18 didn't relapse. Then we want to generate samples where the null hypothesis is true, where desipramine is equally effective as a placebo at treating cocaine addiction. To do this, we can randomly assign each piece of paper to a treatment group. So we have 48 pieces of paper. They either have an N or an R on them. And if desipramine is no more effective than a placebo, it wouldn't matter what treatment we assign to it. So we're not going to pull these 48 people back in. We're just taking the results. And we're just going to randomly assign who got what treatment. Because if desipramine didn't have any more effectiveness than a placebo, then it wouldn't matter which person got the treatment. The chances of relapsing would be the same whether you had desipramine or whether you had a placebo. To be consistent with our observed sample, we'd randomly assign 24 pieces to the desipramine group and 24 pieces to the placebo group. Then we would calculate the sample statistic for this randomization sample. So here's our observed sample, and this is the data. And it's helpful to say, okay, we're going to stop thinking about these as people. We're just going to be thinking about them as information, data that we have. And so don't think like we're gathering all these 48 people together again and then going to rerun the experiment. It's more, we're just taking an Excel spreadsheet. The first column is what drug did you take? And then the second column is what outcome did you have, relapse or non-relapse. And so then we take that information, we put it all into one spreadsheet, and the column where it says what drug did you take, we're just going to randomly assign that to these values of relapse or no relapse. And visually a way to do it is to just take this person, randomly put them into two groups. So we didn't rerun the experiment, we just did the randomization process of randomly assigning the people. So we said, okay, if the null hypothesis is true, it doesn't matter what treatment you receive because the outcome is going to be the same. So with the randomization, we have 16 relapses and 14 relapses with the placebo. And so then we're going to generate a randomization sample statistic, and it's the same process. What we get is this randomization sample statistic, 0.084. And then to get a randomization sampling distribution, which is what we need to do to compare the observed sample statistic against, is repeat this process 1,000 times to obtain 1,000 randomization sample statistics to form a randomization sampling distribution. We just do it over and over again until we get a full distribution. So I'll show you visually how that looks with StatKey. Are we doing a bootstrap or a randomization? Okay, and we have our data up here. So the data is cocaine addiction, desipramine, relapse. We see our original sample is right here, where it's the number of people who relapsed using desipramine is 10, whereas the number of people who relapsed using the placebo is 20. And then we're going to use this original sample to generate a randomization sample statistic. So with this particular sample, it showed that there's no difference. The proportion of people who had the placebo had the same proportion of relapses as the people that were assigned to desipramine. And that's actually what we would expect. If there was no effect, we'd expect no difference. But we run it 1,000 times to see what the distribution is. And so this is our randomization sampling distribution. What we're wanting to do is we're wanting to take our observed sample statistic and see how it compares to the randomization sample statistic. Like how many of these values are as extreme as our observed sample statistic. So you want to know, where does our observed sample statistic fall on this distribution? Do you guys remember what our observed sample statistic was? What was it, Brittany?
-0.42.
Right there.
Right there.
Yeah. Negative 0.42. What we can do is look right here and enter in our observed sample statistic. So here it is precisely. And you want to know how many of the randomization sample statistics are as extreme as our observed sample statistic, and what proportion of our randomization sample statistic are as extreme as negative 0.42. Yep, 0.001. So does anyone know another name for this value right here?
P-value.
P-value. So 0.001 is the p-value of our observed sample statistic. And the lower the p-value is, how does that affect the strength of our evidence? What it's saying is, in a world in which the null hypothesis was true, where desipramine didn't have any effect, if you ran this study 1,000 times, the proportion of times that by random chance you get an outcome of a sample difference in proportions of negative 0.42 is 1/1000th. It's very rare. I mean, yes, it can happen by random chance. You could get an outcome like this, but it's very rare. And so we have high confidence that the difference that we see is a real difference. Desipramine is actually really having an effect. What does that say about our null hypothesis? Our null hypothesis is that there is no effect. What could we conclude about the null hypothesis? Yeah, it's not true. So we reject the null hypothesis.
And we have to write that like on an exam or something, like if it doesn't work with that.
Yeah, you would say, based on the evidence of our data, we would reject the null hypothesis. Yeah?
Is there a specific like cutoff for p-value? Like if it's lower than this number, you reject it. If it's higher than this number.
That's a judgment call.
Okay.
We will talk about sort of what threshold you
Okay.
select, and a lot of times it depends what you're studying. Like if you're studying something that could affect one's life, what type of threshold would you want? You want your outcome to have a really, 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 really low p-value because you don't want to mess with random chance of someone's life. But then in social sciences or something, you can say, hey, if only 1/1000th of the time, which is pretty rare, this is going to be a not true result, I'm okay with that. So right here it says 0.416, but that's just because of rounding error. So this is the observed sample statistic, proportional randomization sample statistics as extreme as the observed sample, p-value of the observed. So the probability of getting a sample difference in proportions is as low as negative 0.416 just by random chance if desipramine is equally effective as a placebo is 0.003. So notice even in the example I did on the computer just now, in this example, the numbers are off slightly because these are just random simulations. So you're going to have a little bit of variation, but to have 2/1000ths of a variation is not worrisome. So to pull us back to p-value, proportion of randomization sample statistics that are as extreme as the observed sample statistic. Visually, this is the area in the tails beyond the observed sample statistic in the randomization sampling distribution. If you know that a randomization sample statistic has 1,000 randomization samples, you could count the dots. You could count the red dots and know what the proportion is. So if you count the red dots and there's only one red dot in there, then you would know what the p-value is, because it's the proportion of randomization sample statistics that are as extreme as your observed one. And then which tails to include, the left tail, the right tail, or the two-tail, those are the three options on the program. That depends on the alternative hypothesis, and this gets to what Brittany was asking. It's our hypothesis that drives which tail we use for our analysis. So a one-sided alternative hypothesis will contain either a greater than or less than sign. In this case, PD is less than PP, and what that's saying is what proportion of the values are as extreme as the left direction of the distribution. Or if you do greater than, it would be on the right-hand side. And then a two-sided alternative hypothesis contains a not equal sign. And you'll probably see an example in the book, and I might be going through an example here. Even with the gender and exercising example, our initial alternative hypothesis was that men exercise more than women, but we could have had an alternative hypothesis that the amount of time spent exercising differs by gender without sort of indicating men do more or women do more. We would just say that they don't exercise the same amount of time, that they're not equal. So that would be an example where you'd use a two-sided. So for a one-sided alternative hypothesis, the p-value is the proportion of randomization sample statistics in the tail specified by the alternative hypothesis. So less than is going to be the left-hand tail, and then greater than is going to be the right-hand tail. And so that's why, in a sense, the equation of your alternative hypothesis is really important, because it just makes life easier. Or if you're given the equation, you would know, okay, this is going to be a right tail that we're going to be looking at. And then for a two-sided, the p-value is the proportion of randomization sample statistics that are in both tails. The difference that we see, it could be an extreme difference on the negative end or the positive end. So let's say we have 100 randomization sample statistics, and we're going to do a left tail test.
Yeah.
And 2 of the randomization sample statistics are as extreme as our observed one. What would be the p-value? 0.0. And how did you get that?
I just took 2 out of 100.
Okay. The fact that you can count the dots makes it more concrete versus like, what's the formula that I use? You know how many are in your distribution. You just want to know what proportion of those are as extreme as your observed statistic. And I think Brittany also asked strength of evidence. The p-value is the probability of getting results as extreme as our observed sample statistic if the null hypothesis is true. And it measures our evidence against the null hypothesis. So here's a range of p-values. So you could have 0.01, and this, it can continue off in this direction, or 0.05, 0.1, or it could be all the way up to 1. The smaller the p-value, the smaller the proportion of randomization sample statistics as extreme as our observed sample statistic. So as you go down and to the left, and as p-values get smaller and smaller, that means it's the smaller proportion that are as extreme as our observed sample statistic. Another way of saying it is then the smaller the p-value, the stronger the evidence against our null hypothesis. So then the question would be, if the p-value is small enough, we reject the null hypothesis in favor of our alternative hypothesis, but then how small is small enough? And this is what Brittany had asked. At what point can we reject the null hypothesis? How small does the p-value need to be? And that's where we'll get into statistical significance. Here's another term and another symbol that's coming up that you'll see a lot. The significance level is the threshold below which the p-value is deemed small enough to reject the null hypothesis. This is a threshold that you get to set. The researcher needs to determine how comfortable am I with random chance affecting my outcomes. So this term is called alpha. So if the p-value of our observed sample statistic is less than alpha, our threshold, then the results are statistically significant and we reject the null hypothesis in favor of the alternative hypothesis. Alpha, our threshold, is something that we set. So before we run our experiment, we need to say, what threshold do I want to have? How low does my p-value have to be in order for me to have enough evidence to reject the null hypothesis? When the proportion of randomization sample statistics as extreme as our observed sample statistics is less than alpha, and so the values of alpha are in the same units as the values of our p-value. So some alpha levels would be like 0.1, 0.05, 0.0001. So when you're looking at p-values and alphas, you're sort of comparing the same things. The thing that we're going to be wanting to conclude is that saying that our observed sample statistic is statistically significant means that we have convincing evidence against the null hypothesis and for the alternative hypothesis. So that's what we're aiming for, is to have enough evidence that we're comfortable with to say, yes, we're going to reject the null hypothesis, which says there's no effect, and actually claim the alternative hypothesis, which says, yes, this difference or this effect that we're seeing is actually real and really happening. Desipramine is really reducing the number of relapses amongst cocaine addicts. So p-values let us know the strength of evidence against our null hypothesis. It lets us know what proportion of randomization sample statistics are as extreme as our observed sample statistic. And so then there's a formal decision of the hypothesis test. And so let's say that as a researcher, I say that my significance level needs to be 0.05. My p-value needs to be 0.05. So the p-value needs to be 0.05 or less in order for me to reject the null hypothesis and accept the alternative hypothesis. So if that's my threshold, 0.05, and my p-value for my study ends up being in this range, and what was the p-value for the desipramine?
0.001.
Okay, so it's 0.001. So would you say that outcome, that result that we observed, the difference in sample proportion, was that statistically significant?
Yes.
Because of why?
Smaller than alpha.
Yes. Okay. Now, does anyone remember, this would be good if you do, the p-value from our exercise and gender study? So remember, our observed statistic was 3 hours, and what proportion of our randomization sampling distribution was as extreme as 3 hours? So it's like 3 hours or more.
Was it 0.4? 2.5?
It was 0.1. I remember Chris remembered it because you're like, that's, 10% of the time we would get this result by random chance if there actually was no difference. And so if our significance level was 0.05, is that enough evidence to reject the null hypothesis? Okay, we would say that it's not statistically significant. When you talk about statistical significance, you're talking about your sample statistic. And so you would say that the difference in mean number of hours of exercising between men and women is not statistically significant. Yeah, we might see some random variation, but we're not going to go out there and make a bold claim that men exercise more than women, because really the evidence suggests that that's not the case, because we can see scenarios where it'd actually be the case that there isn't a significant difference. A formal hypothesis test has only 2 possible conclusions. So after you've set your alpha level and you've run your study, if the p-value is less than alpha, if it's lower than the threshold that you've set, then you reject the null hypothesis in favor of the alternative hypothesis. And the other option is if the p-value is greater than alpha, or greater than or equal to alpha, you do not reject the null hypothesis. because there's sufficient evidence to suggest that we can't reject the null hypothesis, which says there is no difference. I'm going to cover the two-tail. Yesterday when we did the exercise and gender study, we had said, do men exercise more than women? So in this one, we're saying, does one gender spend more time exercising than the other? Our parameters of interest are mean number of hours male students spend exercising, mean number of hours female students spend exercising. And this is where our null hypothesis and our alternative hypothesis is going to be slightly different. Can someone give the equation for the
other hypothesis?
Yeah, the alternative
hypothesis is
alternative. Yeah, the term is not helpful, but the way that I remember alternative hypothesis is like in the social world, people sort of assume things are a certain way. As a sociologist, you come along and say, I think there's an alternative way of understanding our social world. The null hypothesis is conventional wisdom. Conventional wisdom says, there's no difference. But then you as the researcher come along and say, hey, I want to propose an alternative hypothesis to what's assumed. That's the way that I remember it. So, as Brittany said, the null hypothesis for this particular research question would be mu m minus mu f equals 0. Time spent exercising does not differ by gender. An alternative would be that mu m minus mu f does not equal 0. And this is kind of key, does not equal 0, in that we're not making any bigger claim beyond just not equal. We're not saying that one does more or the other. We're just saying, I don't think they exercise the same amount. And then we're going to test that. You would run it the same way, and the only thing that is different, because you still have the same sample, you have men and women, number of hours exercising, the distribution is just the same. You can see here, this is our observed sample statistic, and it appears that 0.109. That was saying, with the first study, what is the proportion of randomization sample statistics that are as extreme as our observed sample, which was 3. And because our hypothesis was saying that men exercise more than women, it was a greater than symbol, so we looked at the right tail. But because with this one, we want to know, is there a difference? Would we expect a difference between amount of time exercising? You click this one, which is two-tail. What it says is, what's the likelihood that we would get a sample difference in means as extreme as 3 or negative 3? Because it could go in both directions. You could have the difference be men exercising 3 hours more than women, or the flip of it would be that men exercising negative 3. Basically, you need to account for both sides of the distribution when you're looking at just general difference in means. And then it's just with these up here that you can indicate, are you looking at a left tail, right tail, or two tail? That is all. Any questions or, all right, thank you guys.